All right, welcome to another coding session. Yes, Bangalang, more Bangalang. I am doing a lot of videos just continually on this one project. I can't remember if I've mentioned this before, but the reason is because maybe I'm being a bit ambitious, but the idea is that I would like to actually use this language to complete a few other projects. Like the next one I have in mind is a rasterizer, and I would like to write the rasterizer in our language Bangalang. So that's why I'm really going into this project. And once I think it's at a point where it's usable, then we can branch out a bit more. But I've got the grammar open here for our language. And the reason is that I looked into doing some more multi-threading. And I do really think that we need to refine our language a bit, give it some more features to really do things well with the multi-threading. And the first thing I would like to add is structs. I do think structs is like a fairly fundamental thing that we need to have. So let's think about what is involved in adding structs. The first thing is that we need to be able to define a struct. That's fairly important. So I'm going to make this struct type, which is the struct keyword, followed by, we have to escape it, and open curly brace. And let's get rid of all this stuff, like that, and then a closing curly brace. And then in the middle, I guess in brackets, we can have multiple members. And the members are like identifier colon type. The type is mandatory. I think that's struct keyword. Oh, we have an or here. Let's get rid of the or. Struct keyword, opening curly bracket, and then optionally we can have some identifier colon types, and then closing curly bracket. I think that looks right. I did want to switch to this big asterisk. Most places we've used, yeah, like this. Yeah, I already had it set up to do it. So now we have a big fat asterisk. Very nice. Okay, so, and that struct type will need to be part of data types. So let's put that like that. There, so we need to extend our data type to handle structs. Now, the next thing is that we need to be able to access members of the struct using the dot notation. We're going to do auto dereferencing here like we do for indexing. So we never need to use the arrow or anything like that. It'll just be a dot. So, and this also brings up another issue with this that I wanted to kind of refine. I would like actually to merge assignment and declaration into the same thing. Let's have a go at that, and I'll explain, maybe while we're at it, I can kind of explain what the reasoning is. So anywhere that we had declaration, we'll put assignment now. Oh, we don't need two assignments in here though. And so I think we could just do this. And I'm going to replace expression with right-hand side expression. And then primary is going to be right-hand side primary. So then, as you might guess, we're also going to have a left-hand side expression. Left-hand side expression is a lot simpler. It's a primary optionally followed by colon and a type. So colon and type, and that's optional. Let's have a look at that, see if that makes sense. Oh. Okay. Probably because I had regex switched on, it was not doing the escaping. So left-hand side, and then right-hand side primary, put a slash in there. How's that look? Better. Put a slash here. Okay. That's more like it, looking more like it. And then instead of variable here, as you might have guessed, we'll put, go away. What the hell was that? Left-hand side expression. So left-hand side expression, and then optionally we can say equals right-hand side expression. That's an assignment. It might seem a bit weird that the assignment part of the assignment is optional. But one of the implicit things in this language, one of the few implicit things, is that if you don't assign anything to it, it's going to assign nil, which means it's basically going to zero out whatever the value is. Now we need a left-hand side primary, which is going to replace this variable business. And the way I want to do it is kind of like, I want to make it a subset of right-hand side primary. So on the left-hand side, can we have a directive? I'm just going to say no. We can't reference. We can't negate. So let's just take all of that stuff out. And this is left-hand side now. So left-hand side primary, we can dereference, we can index. We can't have a nested expression or a call. We can have an identifier. We can't have literals like this. So maybe that's it. It's a left-hand side primary is a left-hand side primary followed by a dereference or an index. Or, I guess we need an or in there. Or it's an identifier. Yeah. Okay. So now that we've kind of, I feel like, normalized that a bit, the thing we need to be able to also do is, as a postfix of the primary, we need to be able to say dot another primary. I think that's a good way to do it. I guess we will find out. I think that should allow us basically to use dot notation to, like, recursively, continue indexing. So that would be dot and then left-hand side primary. And I guess we'll also do that on the right-hand side. So after indexing, we have this other option. Let's see how that looks. Yeah, so it can be a left-hand side primary followed by a dereference, an index, or dot another left-hand side primary. I think that makes sense to me, and same with the right-hand side. So that's quite a big difference to the grammar that we've made there. Quite significant just to support structs, but it's not really just to support structs. We probably could have got away with not doing this actually, but it's something I really wanted to do at some point. So fingers crossed we can manage it. Okay, tokenization. We have a couple of things we want to add. A period and a struct keyword. So we need to make that, we need to put that period in our map. So period character maps to a period token. Cool. I think that's tokenization. There's not much to change there. Parsing. So maybe let's start with the type. We can pass the type. Oh, this is the type here. So we can have the directive of the hat. This is where we actually get into the meat of it. I think I might change this to a switch on the type. So we can do a case like that. And this is like case keyword, I guess. Oh, and that was happy. Okay, I was expecting there to be some sort of syntax or like some sort of bracket mismatch. And then the default case would be, let's assert false and say failed to parse type because we got something we weren't expecting. And let's do another switch inside here. So if I get all this stuff, I'm going to put a case. So if we switch on the value, and the value is proc, then we have a procedure, and we want to handle the procedure stuff. We need to put another default case. So we haven't actually changed anything yet. We've changed them to switches, but it's doing all the same stuff it was doing before. But now I want to make another case. I'm just going to copy this one. But this case is for structs, in which case we expect the struct keyword, we give it a struct type. But with a struct, we want squiggly brackets, not regular brackets. So anywhere we have a regular bracket, oops, let's change it to a squiggly bracket, like so. And we don't need this. This is the procedure return type stuff. We also don't need this params data type, this node, or this. This is sort of like a container for the parameters, but because the struct only has members, we don't really need that extra level of indirection. So I'll call this a member identifier now, and a member data type. We're just going to add it directly to the data type now, and I think that should do the trick. I think that's pretty much it. One thing, let's quickly do it, is I've been wanting to change this. The idea behind this was that you should be able to do something like that. Like you could expect multiple different types, but I never actually use it. So this is like kind of pointless. So let's test my regex skills and do a regex replace. So this dot colon is what we want to keep. So I'm going to do a regex for that and put it in brackets. Slash dot matches a dot literal. Then we want A to Z in capitals and underscore plus. And everything in these brackets should be replaced when we do, or we replace with that when we do $1. So now you can see it's going to change it to dot colon. So I think that should work. Simplify things, and then when we go over here, I think we need to take this and put this here, but we're going to get rid of all these different variations of next token. So the only way we can get a next token is we have to specify a type, and we can optionally specify a value. And if the value was specified, then we verify it. Otherwise, we skip. I think that's about it. Hopefully it's happy with that. This one place where we did not specify the type, we just need to throw it in. So that's the type stuff. Now we need to redo this, which is a pretty big deal. So I think we can just get rid of declaration. And I think what I'm going to do is I'm just going to say that this is the default. You know, if you're parsing a statement, you come across an identifier, then if there's an opening bracket, it's a call. Otherwise, we'll just assume it's an assignment. Try to do an assignment. I think that's good enough. And we can get rid of this parse declaration. Actually, we can get rid of the declaration node type as well. Let's fix that stuff later. So now we have an assignment to parse. The left-hand side, here we have parse variable, which I'm just going to get rid of also. Our parse return, because we reordered it in the grammar, I'm going to put it up here because I like my ordering. So really what we're going to do here is parse left-hand side expression. And this is going to be renamed to right-hand side expression. And it's optional now. Optionally, we have a right-hand side expression. That makes sense. Let's rename this one also. The primary, so I made it so that the left-hand side primary is a subset of the right-hand side primary, right? So I think all we need to do is we should be able to just say, pass in a bool to say, is this the left-hand side? And if it is, I guess we need to pass it on anytime we recurse. And if it is, then we only allow doing these things. So I think it's got all of the post, I'll call them postfix operators. I don't know if that's the right terminology. See, this one here on the right-hand side is exactly the same as this one, and it has identifier. So in this parsing procedure, down the bottom, past this case, there's another case here. These are all the things that come after. The hat, so it's got the dereference, you know, it's got indexing, and we will add the dot notation down there as well. But instead of this big switch statement, the only thing we can do is identifier. On the right-hand side, we can do lots of stuff. So I think we just say if left-hand side do something simple. Otherwise, let's do this big switch statement. Yeah. And the something simple is parsing an identifier. Okay. So yeah, that limits the left-hand side. It means we don't have duplicate code anymore, which I'm super happy about. That was a big thing. So now we need to handle the period. And what is in the period? We just consume the period, and then we have a left-hand side primary. And I think the best way to do this, if we go back to our AST here, like let's say that here we're talking about, if I grab some text, we're talking about like foo.bar.baz, right? Maybe we can take this stuff and I think it's shift, yeah. Move that across a bit. There we go. Foo.bar.baz. So I think what we want to do is we need to have these three identifiers. So they're all for foo.bar.baz. I want this one to be foo, this one to be bar, and this one to be baz. Now that might be kind of counterintuitive, but the way this tree works is that the very bottom one gets evaluated first. I want to evaluate this first so that we get the correct address, And this foo could be a pointer that we want to auto dereference. So we need to do all of this before we then move on to this. So that's why I put this at the bottom and then we go up. So it's a bit counterintuitive, which is why I wanted to like visualize it. And that's why I'm going to do this same kind of pattern here, where I create a new node, and then I make the existing node the child. Is that what I want to do? It's kind of like that, but we're recursing. So let's just write some code and hopefully it becomes clear. So we consume the period. We say this is the child node. Is that what we do? Well, we need to do a parse primary, right? We need to do a parse primary. And that'll give us like the member node. We need to say whether it's left-hand side or not. So we parse the primary, the inner primary, and the member node we want to be the parent, right? That's what we said. So I guess it is kind of like child node equals node, node equals parse primary, and then we add this as the child of what we just got. Yeah, I think that's right. I think that's going to sort everything the way we want. Because this is going to be the member. So like if we're looking at foo, then we parse bar and we get a node back. Or we parse bar, and then as part of parsing bar, we parse baz. Then we get a node back from baz. We add bar as the child of that. And then we pass it back here, and then we add foo as the child of that. This is wrecking my head. So if we have baz, we pass that back, it becomes the parent of bar. Yeah. And then do we pass bar back? We should still pass baz back, right? But then we want foo to go right to the bottom. I don't know that this makes perfect sense to me. So if this is baz, then we're going to return baz. But then we don't want to just blindly add things as direct children to baz. If baz already has a child, then we want to go down. Okay, so I think we need to go like leaf node is node, and for length leaf node dot children is 1. While we've got a child, then leaf node is leaf node child 1, child 0. So that should take us all the way down to the leaf node. And we want to add this as a child of the leaf node. Okay. I think that makes sense. Fingers crossed. Okay. Where do we have issues? This is in the right-hand side expression, so we say it's not left-hand side. Same with this one up here. And this is in the left-hand side expression, so, well, here we need to make a left-hand side expression. Procedure. And figure out what the hell that is. I believe the left-hand side expression is just left-hand side primary with optional type. I've got an extra bracket in there, which is not required. That's better. Yeah, so it's just parse primary, left-hand side primary, and then if we find a colon, that means we have type information. So we consume that colon. And then we say the data type equals the result of parsing a type. I think that's it for the left-hand side expression. So what other error do we have? Okay, so in the for loop, it used to be the 3 parts of the for loop. If I find an example. Here's a for loop. So it used to be like this had to be a declaration and this had to be an assignment. But now that they're both the same thing, they're both assignments. So I'm going to call this pre-assignment and post-assignment. This is kind of tricky. I'm going to leave this here, but it's kind of messed up because we're saying it can be an assignment, but then I'm saying the second thing has to be a colon, which is like totally not right. Really what we need to do in future is have a way of like attempting to parse an assignment, and if it fails, falling back to like maybe this. So this is janky, but I'm just going to leave it as it is for now. So let's go to type checking. And the main thing I think we need to do in type checking is make sure that all of these nodes pick up the correct type. Yeah, we need to make sure they pick up the correct type. So when we define the struct, let's do some example code. My struct member 1 is an I64, member 2 is an I64, member 1 is 1, member 2 is 2. And let's exit with that. So we should get an exit code 2. So my struct, it's going to be, because of this assignment here, actually because we've merged assignment and declaration, yeah, that's the first thing we're going to need to tackle, isn't it? Okay. We're going to need to merge these two. Jesus. Okay. So type check variable becomes type check left-hand side expression, I guess. And this is right-hand side expression. And we can just share parse type check primary now between left-hand side and right-hand side, because parsing has already taken care of the fact that it will only allow certain things on the left-hand side. Parsing will fail if you try to put something that shouldn't be there. So now we can just use that same type check primary because we know only left-hand side stuff is there. That should be fine. We do need to check now whether we do have a right-hand side, because it's optional now for assignments. So we need to do like this. Something I want to get in the habit now of doing is like this. And actually I found that we can just go, this is a nice pattern in Odin. You can just go like that. So if this evaluates to false, it's just going to return false. And if it doesn't, then it'll continue through the procedure, which is exactly what I want. That's exactly what I had coded before, but this is just much more concise. And I like it. And this is return true. Okay. So this should go in here also. So this is saying that if we have the left-hand side didn't have any type information, then we take it from the right-hand side. And if the left-hand side still doesn't have any type information after that, then we have an error. So I think we've like kind of taken care of all of this stuff. Duplicate identifier is not a thing anymore with our merged grammar, because if the thing on the left-hand side doesn't exist yet, we just create it. And if it does exist, then we just reference the existing one. There's no such thing as like, hey, you have to define this. Because we don't, in our syntax now, we don't use this. It's just this to declare B1. There's no differentiation. I might bring that back at some point. But let's just change that actually. So colon equals should just be equals. So what was I trying to get at here? Yeah, duplicate identifier is not a thing. And undeclared identifier is also not a thing. Adding it to our variables is a thing. Maybe that's part of type checking a left-hand side expression. I don't really know. Let's move this up here. I guess also, since we're so anal about this, we should do it. We should order them correctly in these places too. Yeah, just like that. Okay. So if we type check the left-hand side expression, what does that mean actually? Is a good question. What does that mean? Well, I guess if it doesn't, like we were saying, if it doesn't exist in the list of types yet, here we go. We want to do this. So that kind of thing goes in there. Let's get rid of type check declaration. So if, I guess it's just node at this point. So if the node value is not in here, then let's add it. And if it is in there, because now it's possible to put type information, like I could perceivably do like this. It's a bit weird, but it's possible, I think. Having dot notation as well is like freaking me out a little bit, but you can add type information to something that already exists technically with this grammar. And if you did do that, we would just need to make sure that the type information you added was the correct type information. So it's kind of like a coerced type deal. So we kind of need to say like, hey, are these the same type? like that. Oh dear, battery low. Let me pause for a second. Dilemma. Okay, we're back. We're back. We have power. So coerce type. Let's steal some code from here. I don't think we need to resolve. Let's cross that bridge when we get to it. So let's just put these data types in here directly, like so. Failed to type check. Okay, so I guess we could get more specific, right-hand side. But for this particular one, we're talking left-hand side. Yeah, maybe that's enough. You know, we add it to the list of variables if we need to, and if we don't, then we make sure that we're not doing some conflicting type stuff. But we also need to do like I feel like the most important part actually is this, right? We need to type check the primary. And let's do the new style of error handling. Right, isn't that the most important thing? Is it just directly a primary? Yeah, it's a primary. Like this type stuff it's kind of just taken care of by parsing. It puts this type into the primary almost. So then we just need to type check the primary. Does that do some of this stuff for us actually? It doesn't do this. This. No, it doesn't do that. This could even be wrong. I think it's okay, actually. No, I think it's bad. I think it's bad, actually, that it does that. It should only do that. And also it's doing undeclared identifier, which is not a thing. Is there anywhere else that we have that? When we do a call, I think that's actually legit. Oh, and type check variable does not exist anymore. But this we don't need, and this I'm going to say, like, if this is in here, then we set that information. Because in the case that we're doing a declaration, in the case that this assignment is like a declaration and we're handling the left-hand side, we don't want this to set the data type of the left-hand side. The left-hand side might already have type information that we don't want to get clobbered. Yeah. Okay. Is that it? Well, I feel like we haven't really type checked this dot LHS primary stuff. Yeah. Yeah, that's a thing. So if we come across, if we're in the primary and we come across an identifier, then we might have this case, but I think the more interesting case is like, if the identifier has a child, then we're talking about, basically we're talking about a struct. We can probably just do it like else if. And also in that case, it means that we shouldn't have any type information at this point. I think. So I think in this case, what we want to do is recurse in and parse that identifier. So then we should go down to the bottom. Does it need context or something? Does it need anything else? Oh, we want type check. And then what's pointer? So by doing this, we're going to recurse down into here, boop, 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 down to this one. This one, the name should be in here and give us that. So then after this, this child should have the correct type information. And then we should be able to check the members of this guy's type to find, you know, so like we check all the members that exist on foo and we find bar and the type of bar, and then we put that onto this node. That's the idea. Okay. So for, let's call it member. Member data type in this guy's data types children. If member data type dot identifier is the same as this node's value, that means we've found the correct member. And so we assign the data type as member data type. And then we break because we're done. Now this node has the correct type information. So then when we bubble back up to Baz, now this node has the correct type information, so we can look through Bar's members to find Baz. Yeah, I think that works. I think that should put the correct type information everywhere. I hope. We have an error up here. This is where we had declaration before. I'm just so tempted to use this everywhere now because it's so nice. So much nicer. Or return. Or return. Or return. Boom. So much better. Okay. I think that's type checking. Let's see. Now there's a couple of things that we need to do in generation, I think. So the first thing that comes to mind is when we're down the bottom here, trying to figure out the size of something. If that something is a struct, then what we need to actually do is add up the sizes of all the members. And that can be recursive, right? So byte size is 0 for member data type in the children. Byte size plus equals byte size of the member data type with the context. And then we return the byte size. Yeah, so that's a special case for structs to get the correct size of a struct. We have a couple of errors here because declarations don't exist. We're going to have to merge that shit. Yeah, and then again, we need to declare assignment like so. Okay, so declaration and assignment need to be kind of merged. So if there is a right-hand side, we need to generate an expression for that right-hand side. Actually, what we can do is say that if there is a right-hand side, then we get the right-hand side. Otherwise, we get this nil node and use that as our right-hand side. Then I think that kind of covers this. So then we just have this allocation piece. So we shouldn't do that. So I guess we can say, like, if we're only just defining this guy, then we allocate, right? I think that's simple enough. I think that covers all the declaration stuff. So we get the left-hand side, we allocate it if necessary. We say, okay, this is where we need it. This is where the left-hand side is. And then we say, this is what the right-hand side is, and generate the expression, which will evaluate the right-hand side, and assign it to the destination. I think that's right. Oh, and I'll return. We've been moving up here, and maybe reorder it in here. So is there anything else that we kind of need to do when we're in generate primary? We haven't auto dereferenced actually, but that's okay. I don't think we need to do that yet. Is the primary just going to handle it? No, I think it's not. We need to handle the fact that there could be nested identifiers. So maybe we can say, like, if there is a child, then we pass the primary of that child, right? Otherwise, let's just say it's the top of the stack. Like so. Now let's make this a proper if. So in this case we recurse. In this case we don't. In this case, if we've gotten to the bottom of the tree here, that's where, like, foo should be an actual variable, so we can do this variable position stuff and return that. right? This stuff we only need to do at the top, very top level. So now if pass primary, type check primary, I think with the context. Then we want to like add to the offset. I'm not sure why this is freaking out so much. Okay, we want to add to the offset. And we want to kind of figure out like where this member is. What does copy stack address actually return? It returns memory. So I think we could do this actually at the, let's do this in here. So at the bottommost one, we decide whether we're going to return a copy of an address or just a relative address to the stack. And whatever it is, we can just keep offsetting it more. I think that's fine. So now we're going to do something quite similar to what we did in here. Where was it? Down here, maybe? Yeah, this kind of thing. So yeah, we're going to look for the member data type that matches what we're doing. And as long as we don't find it, we're going to add to the offset. So in this case, if we're accessing member 2, then we want to offset by the size of member 1 to get to member 2. So that's what we're doing here. Byte size of that member. I think we passed the context. So I think that should give us the correct offset. Fingers crossed. Let's see. Maybe we can just do that, and then we'll say like that. I think that should work. Oh, that's not happy. Oh. Well, we should be generating a primary, shouldn't we? With the file, the AST node, the context, the register number. Anything else? Contains allocations. Is that? Yeah, that's happy. Okay. We have an issue. Not too surprising. Okay. So the operand data type, I guess, has probably got nothing. Yeah. So what are we actually doing here? We're performing a call. There should be like a name node in here. So we're doing assert b1 equals true. So it's this one here. Interesting. This one didn't have any issues. This one does. So maybe the type information is not getting across here properly during this declaration. Well, I guess it's just an assignment now. So the name node should not have any type information. Let's go back to here where we are. So in here we have an expression 1. Yeah, because it's equals equals, that makes sense. We're resolving the data type. So what is the left-hand side node data type? It's probably struct, is it? No, it's nothing. So the data type of B1 is nothing. Is that right? So let's just check that this kind of, that it would go from here to here. Like in type checking, does it make sense that that's what's going on? Here's assignment. So we type check the right-hand side, and if the left-hand side didn't have anything, then we get it from the right-hand side. Right, so left-hand side is, so this is B1 equals B0, that's this line. So B1, or B0, sorry, should have correct type information. See, it says bool. So then when I step over, left-hand side node should now also have good type information. It is also bool. Step over that, step over that. So then why, when we get to generation, does it not have pass statement, pass? Oh, well, it's in the call line here. Okay, so this is so on this line, this is getting the correct information, but here, this symbol is not adopting the correct information where it should be. Because I put inside here, I do this stuff. Let's go like that. So if it is in there, then we do this, making sure everything's nice. But actually, we should be doing this probably right at the end. You know, because it needs to be after this stuff. Otherwise, we're not going to save information that was inferred from the right-hand side. Okay. Still getting a lot of errors. Could not determine type of B1 at line 17. Okay. I feel like it was determining it before. And I guess it's this. So that's B1. It's got no type information. That was at line 17, right? B1. So that's B1 equals B0. Pretty sure that's the only place that shows up. Yeah, line 17. So if the right-hand side node has a data type, oh, it doesn't have a data type. What? Well, I guess it couldn't infer it from the left-hand side now. But this guy should pick up a data type. So it should be like when it goes into type check primary and we find an identifier and it doesn't have children. So it should go into here. Should go into here and put the correct type information, right? I feel like it should do that. Let's see what happens. So this is B1 equals B0. And we've gone past the right-hand side. And we didn't hit this. Why not? Is my condition not right? Yeah, it needs to be in there. So why would it not be in there? The way that it gets in there, is when we type check an assignment and we don't find it in there, then we put it in there. So when does that happen? Let's check that. This should be, I think that should be left-hand side node because I copied it from somewhere else. Yeah, okay, let's see if that made a difference. Okay, now we're going into there. And now the left-hand side node data type is bool, which is correct. We're getting byte size of probably an empty data type. Oh, number. So we're doing an assignment. And the left-hand side does not have a data type. Okay, and what is the left-hand side? It's member 2. Okay. So we're on this line. Member 2 does not have a data type, apparently. No, yeah, it should have picked up the data type, right? It should have picked up the data type when we did what I thought was some recursive stuff in here. So let's see if this ever gets triggered. Nope, it appears we never go in there. Well, let's try something a little more lenient. Do we get to here? No. The identifier never has children. So when we're here, we're talking about the left-hand side node, which is the member 2. So it should have a child, but it does not have any children. Okay, we're talking about a left-hand side expression. But I'm in the left-hand side expression, type check. So it's during parsing that we create that sort of tree, right? Do we not? Here we're assuming that we have a tree. No, it's because it happens down here is where it should happen. So here the node is member 1. The child node is empty string. Huh. Whoa. That looks like some corrupted shit right there. Oh, is this pointers? No, this node is not a pointer. How did that get so corrupted? What is leaf node? It's member 1. How did this child node get all... Oh, there's 2 child nodes. Oh, that's a negate. And that's a C string. Okay, this is the one. This, I guess there's multiple child node variables and they're all showing up in the debugger. That's a bit weird. So this one looks right, actually. And they should not have data types. But like it looks like, I mean, if I skip over to here, node is member 1 and it has, doesn't have any children. Huh. Didn't we just add? Oh, because leaf node is a copy. Leaf node should be a pointer. Let's try that. And then step over. So then node is member 1 and it has 1 child, which is my struct. Okay. So I feel like we've created it correctly now. Oh, and we have Xcode 2. If I change that to member 1, Xcode 1. All right. Let's have a quick look at the assembler. So we allocate 16 bytes and nil initialize it because we don't explicitly assign anything, so we set it to nil, and it's 16 bytes because these are 8 bytes each. So the whole struct should be 16 bytes. That's correct. This here didn't throw an error. I'm just going to ignore that. That should have thrown an error. Okay, so this is allocating when it shouldn't. I guess we also need to make sure that it doesn't have children. And because if it has a child, that means it's just a member we're talking about. And we don't want to allocate members, right? See, that's better. We don't allocate members. So on the top of the stack, we assign 1, and at +8, we assign 2, which seems correct to me. Member 1 should be at the start of the struct, and member 2 should be 8 bytes further into the struct. So those assignments look good. Now we do a call, so we allocate some space, and we copy the variable in, which is RSP plus 24, which I guess is correct because we get the right answers. Then we call exit like we would normally. All looks good. So a couple extra tests we can do, and I pray that they work because we're getting near the end of the video. If we say that we want a proc, unfortunately we don't have, like, I want to add some form of type aliasing. So you should be able to do, like foo equals that. And then you should just be able to use foo here. That's, I mean, you shouldn't have to repeat this struct manually every time. Let's leave that commented out. That's something we really want to add. But at the moment, we just have to specify the whole struct every time. So we pass in a struct, and we do that like that. So that should work. And it does not. Unsupported byte size. Null type information. Copy, so generate expression. Generate call. I mean, it must be this, right? To start with, that should be like that. I don't think that would be it. Oh, that was it. So that, so you can have undeclared identifiers. You can still have undeclared identifiers. At the moment, because we don't explicitly check for them, we just get a stupid error. We'll fix that later. Then the last thing really, oh no, we didn't do auto dereferencing yet. We haven't done auto dereferencing. That's okay. We can do that another time because we're already nearly an hour 15 in. And I'm pretty happy. It was a bit of a monster, right, to get it working, but we do have structs. We can create a struct, we can assign to the members of a struct, and we can pass it around and access the members. I feel like that's the main thing. I'm not going to tempt fate and make a recursive struct right now, like where a member of a struct is a struct. But in theory, that should work. Maybe, but there's probably a bug, so I'm not going to test it. And that's where we're at right now. Okay. I'm pretty happy with that because we've got structs and we also got this kind of more unified assignment expression business going on. I do eventually want to take this procedure and merge that into here as well, because that's really just an assignment as well. But we're really going to have to up our parsing game for that. So yeah, pretty happy with that. Struct business. That's enough for today. Thanks for stopping by. Have a good one. Ciao for now.